Well, thank you. Um, we'll see how I do. It's been a long time since I've given a public talk, and last time I gave a talk, there was those glass water bottles, that they have in Europe and everything. And I was gesticulating wildly, and it flew out into the audience and shattered. So I don't think I could be any worse than that. So, yep, I'm Ben. That's what I look like. You can also look over here, and that's me 2 kids ago and 6 years ago. So longer hair, maybe some grayer hair. I'm an engineer on the Elasticsearch search team. So grab me if you want to talk about search things, vector search relevance, scaling stuff, blah, blah, blah. And I also work a lot in Lucene. So if you have Lucene lower level questions or anything, I'm somebody to talk to. So this is what we're going to go over today. And apologize ahead of time. There's a tiny bit of math and a lot of puns. A lot of bit puns, a lot of barbecue puns. Puns aren't your thing. Very sorry. All right, so first, why do we need to make vectors cheaper? So fast vector retrieval, there are many, many different kinds of vector indices. And generally, some of the fastest ones are graph-based. Now, graph-based are fast because they have logarithmic search scale, meaning to search for millions of vectors, you only have to do thousands of vector comparisons. And so they can get to your answer very, very quickly. Here's a little graph image of what HNSW looks like. But all graph-based algorithms sort of do this in a way where you have this space that it can explore very, very quickly and get to your answer fast by doing very few vector comparisons. But generally what this means is that it is searching over your vector space very randomly. And so it's not getting big chunks of things to then compare against. It is looking at individual vectors a lot, and it is doing it random search with a random seeking all over the place, which is okay, but for the programmers out there or the systems engineers out there, you may recognize this sheet and this table. This was published by Google a long time ago, and a lot of the numbers have changed in recent years, but the scaling is similar. And so let's talk about the difference between what it takes to randomly seek inside of a graph. So you have this first number, if everybody can see, is this main memory reference. That's how long it takes on a scale of 100 nanoseconds in this imaginary scale. You can read something from main memory. For reading from an SSD, it is a 200x increase in cost when you have to seek and then read from disk a random spot to then load it into memory and then to read it. And so for search patterns that are very random, this is your cost. So if only there was a way to make vectors smaller and cheaper. So let's talk about what quantization actually is. And this is it's a general thing. A lot of people think about it as just for vectors, but it's a sort of a general thing. So quantization is the idea of you taking something continuous or higher fidelity and discretizing it or bucketing it or making it lower fidelity. The idea is you keep the important stuff and you throw everything else away. So here's a very simple representation of a continuous stream of information, and then you can see how it's discretizing into buckets given some sort of error bounds. And this allows you to store fewer pieces of data for a continuous stream. So it's common in signal processing. Here's another type of quantization. So you have this image of a cat. We can all see it's a cat. It's not too blurry on the screen. People in the back, can you see it's a cat? It's a cat? Yes. All right. We can make it cheaper by quantizing the pixels and making sure we only store a couple of the colors. And yeah, people in the back, is that still a cat? Yeah, you can still see that it's a cat. So we're keeping the important stuff, but we're making it much cheaper to store. So, I mean, if only we could do that for just buckets of numbers, and well, we can. So we're going to do a flyby and wave at scalar quantization. All right. So models are inherently lazy. I love ML researchers, but generally then they hand it off to somebody who's going to make it actually run. So when you have embeddings, when they give you float 32 per component, by component I mean dimension, a float 32 can store 4 billion values per dimension. So it's B with a billion. So 4 billion. So it's like 2 to the 32, give or take some special cases depending on your architecture, blah, blah, blah. This modern art piece is the printout of some embeddings from the Cohere v3 model. These are just what the numbers are, and you can see that it's all between about negative 0.15 and positive 0.15. We're definitely not using all 4 billion options per dimension. And so we're using like a very narrow window, and many transformer model bases, like transformer models, end up looking like this. And so to drive the point home even further, here's some box plots for some of the dimensions. And honestly, it seems like it's not even anywhere near the negative 0.15 and positive 0.15. It's more like between 0.05 and negative 0.05 that you actually care about for those model dimensions. So if only we could throw away all of that extra information. And we can. So this is basic scalar quantization. You can have, this is a distribution, a real distribution of real vectors that we just saw. You can see the negative 0.15 and the positive 0.15. And all distributions, not all, but generally for transformer-based models, this is the type of distribution you end up getting. Looks very like, okay, there's a high concentration towards one particular center, and then it fans out. This is the distribution scalar quantized. And I mean, people in the back took your glasses off, you couldn't see the difference. So you take these floating point values that give you 4 billion options and require 4 bytes to store. You do a simple min-max normalization with some quantiles for your minimum maximum. And then you end up getting bytes, which you only need 1 byte to store. And that's a 4x reduction. And then you can take it even further and do half byte reduction. And that's an 8x reduction in space. The accuracy loss is very small. For int7, you talking about for brute force search, it's like maybe 5% recall loss, which honestly, you grab me after the talk and I can talk about why I hate measuring recall. And you really should measure accuracy in your search versus what you want to search for, not necessarily recall. And it allows faster search because there's fewer bytes to read off disk, fewer bytes to read on heap, fewer bytes to compare. And it's a perfect fit for Lucene. Lucene's a segmented architecture, which means if your distribution shifts or we need to requantize something, we have times and moments where we can do that. So none of this would be possible for data that's real, that's being updated all the time, unless you had some sort of segmented architecture. So there's a but. So this is how many bytes it requires, how many megabytes it requires, and man, it's really hard to see for your people in the back. I'm sorry, but it's about 2 gigs for float 32 for 500,000 1024 dimension vectors. And then for int4, it's about 300 megabytes, which is, hey, you know what? 300 megabytes for 100,000 vectors is great. But you know what? We want to do what about 100 million? We don't want 100,000 or 500,000. We want hundreds of millions. What is this going to take? And even for int4, this is still like 50 gigabytes of RAM for you to have for the random seeking all over the place. I am not made of money. Elastic pays me very well, but I'm not made of money. So having to pay this much is like, okay, can we make this even better? And so what we're going to talk about is a little bit of binary quantization. Let's see if this video runs. Okay, here we go. It runs. All right. Sorry if people in the back, if you can't really see it. But this is what binary quantization does, is it allows you to take a floating point number, reduce it to a single bit, and then now you can have 8 floating point numbers into 8 bits, which then store into a single byte. So I have the text here. I hope you can see that. So you have 8 times 4 bytes, which is 32 bytes, down to 8 bits, which is just 1 byte. So it's about a 32x reduction in space. What this actually means for that example I gave before, 500,000 vectors at 1024 dimensions, you require 66 megabytes to store of memory, which is, I mean, that's way better. And then for 100 million vectors, that's 12 gigs, which is kind of amazing. You can start doing stuff on a single node that you could never do before. However, there is a problem. For naive bit quantization, this just falls apart for many, many models. There are very few models where you could just do this and continue to get acceptable recall without oversampling by a lot. So here's an example of a model where this does extremely poorly. This is E5 small. E5 is a pretty decent open source multilingual model. We have it native in our stack. We have some optimized builds of it that work well in Elasticsearch. But you can see all my statisticians in the house. When you see that distribution, you shake your head. You say, man, that correlation's really bad. In fact, it's so bad that your re-rank costs end up being, you have to query 80 to 100x more vectors than you would actually need to get the top 10. So let's say you wanted actual top 10, you would need to query 800 or 8,000 vectors, then re-rank them with the raw floats to then get the same that you want. Like, it just doesn't work. And one of the reasons that it doesn't work well with this model is its distribution space is very narrow, and it doesn't perfectly center around the origin. You saw before where we're pivoting over 0. So we're pivoting over 0. We're going, if you're above 0, you're a 1. You're below 0, you're a 0. This means if your vectors do not center around 0, you're up a creek. It's not going to work for you. And so one of the questions then becomes, let's just not use 0. Hey, I know how to cluster things. Let's use a centroid. Well, this becomes dangerous, and I'll talk about how to get around this in a minute, because now what you're doing is you're comparing vectors that are centered on a centroid, not the vectors themselves. And folks who know linear algebra will explain to you why that doesn't work. But luckily, linear algebra is also to the rescue. Now we're starting to get to some of the more important, better bits. So this is the better binary quantization. 8.16 just released. It's also in serverless. So I'm going to talk about solving the centroid problem that I just talked about. Asymmetric quantization, which is a thing that a lot of people don't know exists, but it's been around for a while, and I'll talk about how we use it in this, and a little bit of interesting bit packing, which is going to be really difficult to get through, but we'll do it together. And if I don't explain it well, please ask me questions. All right, the centroid problem. So if all vectors are centered around the centroid, you can end up shifting them around, and you can see how they become part of the unit circle. Sorry, people in the back, if you didn't see that animation. I'll play it one more time if it works. All right, so these are 3 vectors, and then you can see its centroid, and then we normalize it around that centroid. And you say, Ben, hey, you just said this is a big problem. How do we fix this? Well, I actually did this. I actually grabbed my old linear algebra book from the bookshelf. I still have my old college notebooks. I spent hundreds of dollars on them. I can't give them up. And I double checked this math and was like, can we do it this way? And yes, you can. So here is the distance estimation for vectors centered around a centroid. And it actually ends up expanding to where you have these corrective values, which can be calculated per vector and then stored separately. And then you can estimate it with a quantized dot product. We can work out the math together if you really, really want to. But everybody else, that's it. All right. So asymmetric quantization. So how we get the better storage is we do quantize to bit. So remember, 8 floating point values into 1 byte. So that's 4 times 8 is 32. You're going down to 1 individual byte. And we then store some of those corrections I mentioned before that help us with the estimation now that we're centering on a centroid. But since we're centering on a centroid, this means that we actually don't need to quantize the queries to the same amount. We can quantize the queries to only int4. And this means that when we do a comparison with the int4 values and the stored bit values, the higher level of quantization or let's say high level of fidelity of the query vectors allow us to retain more information at query time. And being able to center around the same origin is what unlocks this. Because if things aren't centered appropriately, or if your vector distributions change significantly, or you're quantizing it in a weird way, this doesn't always work. But generally, if your numbers are centered appropriately, you can do this. And you have, as I said, more information at query time. I'm getting ahead of my slides. Maybe I just need to click faster or talk slower. We'll see. So dot products against bits are exceptionally simple. All right, remember, we have our int4 numbers, and then we're querying against a bunch of bits. But these bits are stored in a single byte. And so does that mean I have to expand and then compare and blah, blah, blah? So, oh man, I'm sorry for people in the back. I was hoping we'd have a bigger screen. There's really, really small numbers. But what it ends up being is that you have your ones and zeros that are stored in the byte. And then you have your int4 values that are per dimension. And it ends up being you treat the byte value as a mask. So it ends up being what's 0 times any number. Everybody know, what's 0 times any number? 0. What's 1 times any number? That number. So that's what you end up getting. Now, it's kind of bad if you would have to expand all of these stored bytes into their ones and zeros and then multiply by 0, then multiply by 1, then multiply, and then sum all that together. That's a lot of wasted compute. But, and there's going to be, this is one of the trickier parts of the talk. So if I do this poorly, I'll update it, and then just ask me questions after. All numbers in a computer are just bits. And since we're scalar quantizing, it's very simple ones and zeros. There's not floating point or anything. We don't have to worry about a mantissa, exponent, blah, 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 blah. We have ones and zeros. So for a 10, that is 1, 0, 1, 0, right? If you expand that out, that's 0 times 2 to the power of 0, plus 1 times 2 to the power of 1, blah, 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 right? So you're bit shifting all the different individual bits, and you can expand it out. Well, if you expand it out and then apply the individual bits from your stored byte, lots of bits and bytes, you can optimize it. So this is how we actually do the packing. The blog on this has been released, so if you want to look at a lot of these images that I'm sharing, go to our Elasticsearch labs, and it's there. But what we take is the 0th bit, so the lowest power of 2, of all of our int4 values, and we pack them all together in the same bytes. And so for simplicity, this is only 1 byte for each one, but you could have many of these. So you have a series of bytes that are all the 0th point. And then you have the first byte or bit. And then you put that in the next one, so on and so forth. All right, so we have these 8 half byte quantized values, and then you compress them all down into 4 bytes. Okay, don't fall asleep on me. We're getting there. All right, I promise we're getting there. And so now the dot product ends up being bit operations, because we can treat each of these individual compacted values and then do a bitwise AND between them, because it's all just 0 times the 2 to the power of 0, all summed together. And so if you just do a bitwise AND, you keep the ones that they have in common, which is what you would have when you did 1 times 0 is 0, 1 times 1 is 1, right? It's a bitwise AND. Computers are really good at bitwise ANDs. So we can do that, and then we shift everything back to those power of 2s. That's what those little carets mean, the little shift signs there in the middle. And this is what it looks like in naive Java. Now the code looks a little bit different than that, because we do a lot of SIMD optimizations to make sure we're using the CPU, but that's what it looks like, which honestly, that doesn't look too bad if you knew what you were looking at. I imagine if people who don't write Java are slowly dying inside because they hate Java, which I don't have a choice. All right, so here's some real numbers. And when I made this chart, again, I was thinking I would have a bigger screen, and I apologize for all the people in the back. But what this essentially boils down to is that you have 100 million 1024 dimensional vectors go from requiring over 400 gigs of RAM to, I have to squint on my screen too, 14. So on a, what would normally take, I don't know how many nodes, you got, 48 gigs of off-heap RAM, maybe that 46, and this 400, so it's like 10 nodes. Oh crap, I gotta have replicas, so times that by 2, and so now I have 20 nodes. And then here, we're down to 14, which fits on one node, and if I turn on replicas, now I have 2 nodes. That's pretty good. And so here is some numbers on how long it takes to index this. The green is BBQ, the blue is float, and this was ran on my MacBook. So across the board, BBQ is cheaper to create the index, mainly because vector comparisons are much faster because we're doing bitwise and there's much less data to have to read on heap or to pull into cache to do comparisons. All right. So Ben, how does it fare on the recall side of things? For recall, compared to our other scalar quantization, I mean, yeah, it's a little bit worse because we're storing a single bit. I mean, come on, not everything's free. But you can end up achieving better recall by oversampling, by meaning you're gathering 2 times as many values as you really want and then re-ranking them. And we're working on a way for this to be done automatically for you in an optimized fashion so you don't ever have to worry about it. But, if you give engineers an optimization problem, they will never ever ship anything. So we just got to ship, and so we shipped it. And so if you do the oversampling and re-ranking yourself, you can achieve pretty good recall. So let me talk about this one more other way. So we have in case you didn't know, so Elasticsearch has this thing called Rally, which allows you to do benchmarking against Elasticsearch clusters. And we have a medium to large vector benchmark, which is 134 million documents of 1024 dimensions. And so here, this chart is the K that I'm searching for, the number of candidates I used to search for HNSW, and the re-rank that I used globally. So this wasn't per shard, it was a global re-rank. And we're doing some more benchmarking that sort of shows that maybe local re-rank's better, but we'll see about that in the future. So here you can see the importance of re-ranking. So the one in the middle, you got to 78 of NTGC. So what I mean by that is for the model giving you the most relevant results, 78% of the time, you got what it considered the most relevant results every time. So this shows that with this method and with most other quantization methods, the vectors that are actually nearest, that the model thinks are actually nearest, still bubble up to the top. So, but you see that the recall without any sort of re-ranking is about 50%. All right, and this is with all the cost of HNSW now. So now you have 2 levels of approximation. And this is why I think recall, while it's cheap for us to measure, generally you want to know the vectors that are actually close to your vector. Having that long tail of recall 1,000, don't necessarily care about that all the time. But you can recover it by oversampling and re-ranking. So you can, and this is, I forgot to say, this is on one node. So this is 134 million documents on a single node. And so these QPS and everything is all just a single node. So here you get about 9 milliseconds single query latency, and you get about 1K QPS on a single node. And then for some re-ranking, you get about 18 milliseconds individual latency with about 450 QPS for multiple clients at the same time. And then if you really want to re-rank, it bumps up to 50 milliseconds and about 160, 170 QPS. And again, if you want to make this faster, you add another node, and then you double your speed because it can all hold in memory. All right, I'm running out of time. This is my last slide. All right. So some of the more educated people out there who are nerds about vector search know about this thing called product quantization. And he's like, Ben, product quantization already does this. It's been around since the 90s. People know it. Why are you doing something different? Because product quantization is freaking slow. It is so slow to build an index. And the reason is because it has to build these clustering code books. So product quantization can achieve 32x reduction, and it can achieve higher levels of reduction if you really, really want it. And it can achieve great recall at 3 to 5x oversampling, like we were just talking about. So why did we go with BBQ? And the reason is we did an apples to apples comparison. We created product quantization in Java. We optimized it as best we could. We spent like a month working on it. And we spent a month working on BBQ, optimizing it, same people, making sure that we can do an apples to apples comparison in situ. And what we found is the quantization time is like 10 to 50x slower for product quantization. Like it is so bad. I cannot, like it's so bad we couldn't do the large scale testing on it on a CPU. Like you can't do it. There was a larger scale test that we were trying, and BBQ finished it in a couple hours. And I let it run for a day with PQ, and I just turned it off. And I was like, I'm done. I'm not going to test this anymore. So from what we found, product quantization is 13 to 50x slower on the building the quantized code books and everything. And then at query speed, discounting how long it takes to find the quantized values, because to build the code book with PQ, you got to do a bunch of centroid comparisons, blah, blah, blah. Discounting that, BBQ is still 2 to 3x faster at query time, and we can probably make it faster. Mainly because for generalized PQ is it's all table lookups, and you can only make that faster by so much. Yep, that's it. I went over by 2 or so minutes. Yeah, and I have questions, and it says answers, but really it'll be responses. Sometimes I don't have all the answers. Thank you.
Thank you all. That was wonderful. We're going to be kicking off our Ask Me Anything in a couple of minutes, but come find Ben for questions, and we may have some extra time for questions for Ben.